Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. We're going to learn something new today, some reactions of organometallic compounds. There will be four main reactions that we're going to study. One is substitution reaction, the second one is insertion reaction, the third one would be oxidative addition, and last but not least would be reductive elimination. So these four chemical reactions are important reactions involving some organometallic compounds. So from the names of the reactions, we can tell that there will be involved loss or gain of ligands above, molecular rearrangement, formation or breaking of bonds to the metal, or the ligands themselves. So we're going to see that one by one. So we're going to start with substitution reaction in carbonyl complexes. So this is a typical substitution reaction. I'm sure you have seen and heard this term before in some of the courses. So we have ligand here, L is ligand and with metal, and we have 5 carbonyl here. You can always substitute carbonyl with some other ligands, which is denoted as L prime. So this is the general equation where you can refer to. For example, we have iron, pentacarbonyl, and we want to attach your iron with the phosphine, with trimethyl. So this is using some heat, and you're going to get your phosphine here, replacing your carbonyl, and then carbonyl is going to be one of your byproduct. So this is called substitution reaction. This is used especially when you want to introduce new ligands into complexes. So for this type of reaction, there will be no change in terms of oxidation state. The oxidation state of your metal, in this case is your iron, will remain the same throughout the whole process. Be it reactant, be it product, there is no change in terms of oxidation state. So that is substitution reaction. Substituting the existing ligand in your metal complexes with the new one. So, according to kinetic studies, there will be two important processes. This one also you have gone through earlier in some other chemistry courses. You can have slow step, you can have fast step. So, slow step is called rate determining step. This is where your intermediate species will be produced. So, look at this first one. We have it can be associative or it can be dissociative mechanism for substitution. Depends. Let's look at the first one. We have this molybdenum with 6 carbonyl, and we want to introduce this ligand. So for the slow step, your ligand will be attaching directly to the whole complex. So this is called bimolecular reaction. And then for the fast step, your carbonyl will be removed from the whole complex, producing 5 carbonyl with 1 new ligand. Okay. So the rate determining step involved bimolecular reaction of molybdenum with the newly added ligand. Now the second example would be dissociative mechanism. So dissociative means the first thing first that your complex do or does is breaking the carbonyl away from the metal. So instead of having 4 carbonyl here, we have only 3 here because 1 carbonyl has been taken away. So now it is ready to take 1 more ligand. So this is newly added ligand. So you're going to have nickel CO3L. So most of the substitution reactions proceed primarily by a dissociative mechanism, meaning most of the substitution reactions taking place through dissociative mechanism, but we can have associative mechanism as well if the metal is large, meaning they are providing favorable sites for incoming ligands. Right? We have large sites, large metals, so there will be more coordinating sites. And second, when the ligand is highly nucleophilic. Okay, so this is your first task today. You have to give me the definition of nucleophilic ligands. And please give me 2 examples of these nucleophilic ligands. Okay? Moving on, so you are done with the first one, which is called substitution reaction. The second one is called insertion reaction. So just now we learned substitution reaction where the existing ligand can be replaced or substituted by the newly added ligand. There are two mechanisms: dissociative mechanism, associative mechanism. Both are working in substitution reaction, but the most favorable one would be dissociative mechanism. Associative mechanism can take place, but you must have large metals where there will be more coordinating sites. And second one, you must have nucleophilic ligands. Okay. Now the second reaction, insertion reaction, this is by inserting small molecules X or Y into your metal ligand bond. It can be M2C bond, it can be M2H bond. So although some reactions are believed to occur by direct single step, but actually in the real life, in the real experiment, it could be much complicated than that. So there are two types of insertion reaction. Just like your substitution reaction, there are two mechanisms. But for insertion reaction, there will be two types. The first one is one insertion. So from the name itself, it suggests that there will be insertion bonds where it will be occurring only on one atom, as shown below. So we have carbonyl here, and then carbonyl here now is being attached by not only oxygen but also metal. So this is 1-to-1 insertion. The second one is called 1-2 insertion. On the inserted molecule, the insertion bonds occur on two different atoms. So 1-to-1, one atom, 1-to-2, two atoms. So how does it look like? Look at this cobalt with 4 carbonyl and then 1 hydrogen. Now we have these ligands, these new ligands. And this is the second task. Can you name this ligand? What is the name of this ligand? But the thing that I would like to emphasize here is that we have two carbon here. So these two carbon will get involved in the formation of new complex. So two bonds here, carbon and also carbon prime. So this one is called 1-2 insertion. So there will be two ligands mainly involved in the formation of in this insertion reaction. You can have carbonyl insertion, or we call it carbonylation. So before this, we have gone through carbonylation, where you just pass through carbon monoxide gas into the flask of your reacting mixture. Now, for example, we have when CO reacts with an organometal, we have CH3MnCO5. So we have methyl, we have metal, and we have carbonyl here. And the product was CH3COMnCO5. Okay, when we react carbonyl with this complex, we get CH3COMnCO5. So what do we understand from this reaction? So the first one we see, this is that the CO has inserted itself between Mn and CH3. So meaning CO now is located between metal and your methyl, producing acyl complex. So acyl complex. Can you name this? Can you tell me why we call it acyl complex anyway? It is acyl or acyl complex. Acyl complex. However, upon further investigation, when it is labeled with 13 carbonyl, we found that, well, actually CH3CO is already there, and CO4 with the newly added 13CO. So the conclusions of this study are, the inserted CO is actually previously coordinated to the metal, meaning the one that formed acyl complex is not coming from the newly added carbonyl, but actually from the existing carbonyl that you already had in your complex. So the acyl carbonyl is not derived from the external CO. This is not the newly added CO, but actually this is the one already coordinated or complex with your metal atom. So the second one, the incoming CO is added cis to the acyl group. So the incoming CO, if you have newly added carbonyl, that particular carbonyl will be located in which it is cis to your acyl. We're going to see the structure below. So this is your acyl, CO bond O, carbonyl with methyl here, and the newly added CO is L is actually cis to this acyl group. And the third one would be this can happen to any Lewis bases. So any Lewis bases or any type of ligand that behave as Lewis base can bring about carbon monoxide insertions as shown in the mechanism below. So therefore, the conversion of alkyl to acyl can be affected by additions such as phosphine or any Lewis base. Okay, so this is carbonylation. You have manganese complexes with methyl or methyl here. So you have solvent. Then definitely you have newly added carbonyl here or carbonylation. So the newly added carbonyl will not be added directly to your methyl. So the formation of acyl here is actually happening because of the existing carbonyl is moving from here to here. Okay, and the newly added ligand will be added, in which you will be cis. This L will be cis to your. That's the best way where I can explain the formation of your complex through carbonylation. So we have gone through carbonylation, adding carbonyl. The second one would be sulfur dioxide insertion. So unlike CO, so sulfur dioxide inserts directly into MC bonds. What does it mean? Okay, so you see this is the structure of your metal complex C directly bonded to M metal, and then your sulfur dioxide will be directly attached to your carbon. So there is no formation of acyl complex, no such thing. So it will be directly bonded to your carbonyl. So forming and rearranging themselves in such way to form your sulfur dioxide complex. Now the products of sulfur dioxide complex after SO2 insertion can be varied. So it can be in this form where sulfur dioxide directly inserted to your metal, sandwiched between metal and also your alkyl group, whatever it is. Or it can be sulfur directly attached to your metal again, but now your R is not attaching to your sulfur but to your oxygen. Or it can be oxygen directly attached to metal, or oxygen to oxygen bridging metal and also sulfur. So from the structure itself, we understood that the coordination number of metal would be higher now for the complex. By the way, what is coordination number? You have learned this in inorganic courses. So this is another question that you have to explain in your comment on the Padlet letter. So, but even though the coordination number increases, but the oxidation number of your metal does not increase at all. Okay, but if it does increase, there will be another type of reaction, which is called oxidative addition reaction. Okay, this is our next reaction. So we have learned two types of reaction. The first one is carbonylation. The first one is substitution reaction involving carbonylation and sulfur dioxide. Carbonylation and sulfur dioxide reaction. And the second one would be on the. So we have learned two types of reactions. One is substitution reaction. The second one is insertion reaction. So under substitution reaction, we can have dissociative or associative mechanism. It depends. And the second one, we learned about insertion reaction. Insertion reaction can be happening into ways whether we are adding carbonyl or sulfur dioxide. Now we're going to learn the third type of reaction, which is called oxidative addition, OA reaction. OA is the notation for oxidative addition. So when we call oxidative addition, there are two things that we need to understand. First, there will be an addition reaction, and the second one, this reaction will involve some change in the oxidation number. So that's why it's called oxidative addition reaction. So low valent transition metal complex reacts with the molecule to produce another complex with both oxidation number as well as coordination number increased. Okay. So for this type of reaction to proceed, we must have number one, the metal center must be D2 or greater, cannot be less than that, or else there will be no oxidative reaction taking place. And the second one, metal center must be coordinatively natively unsaturated, meaning it cannot be too saturated. When it is saturated, there will be no sites, no place, no angle for the newly added ligand to be attaching to. So you must be having a complex that is not really saturated. Okay, and then the number one, it must have both appropriate and empty orbitals. Definitely, if you want to receive more electrons in the complex, you must make sure that you have empty orbitals, because only orbitals can hold your electrons. So the compound must have less than 18 electrons. We have learned EAN rule, effective atomic number rule, that you cannot have more than 18 rule. So that's why in order to form oxidative addition, the reactant that you want to use must be a complex with EAN less than 18 electrons. The completed one, the newly formed complex, then should be having 18 electrons. Now look at this example. We have iridium. This is viscous compound. We have phosphine. We have chloro. We have carbonyl here. So this is one oxidation state. It is D8 for coordinate, as you can see. And this one, iridium, we added two more ligands. Now it becomes 6 coordinate. Only then you will get 18 electrons. So now let us make some revision on the IR frequency. For 16 electron iridium, it is 1967. For iridium 3, the oxidation state increased. It is 2075. So stretching frequencies tell us the strength of the bond. So the higher the frequency, the stronger the bond. So from this frequency itself, we understood that with 18 electrons, with 3 oxidation states, your iridium is actually stronger than iridium 1. That's number 1. But why? Why is it so? So we have also gone through this, we have learned this. So the bond strength or the bond order increased because there is lower pi back bonding. Why there is lower pi back bonding? Because there is a decrease in the electron density on the metal. Definitely. Okay. So when there is decrease in electron density, there will be lower pi back bonding, bond order and bond strength will be higher, and this will be translated in the stretching frequency. You're gonna see higher stretching frequency when the bond order or the bond strength increase. Okay, you can see this diagram below. Now let's look at this bi-molecular example. So we have Mn to Mn bond. Can we break these two? Yes, we can break this into two individual complex when we add Br2. So you're going to get two newly formed complex. So this falls under oxidative addition. Now the last one will be on the reductive elimination or RE reaction. So from the name itself, definitely you can tell it is opposite to oxidative addition. You add new ligand and then the metal will have some change in the oxidation state, meaning from lower state to the higher state. When it comes to reductive elimination, RE reduction, it's going to be the opposite. You're going to eliminate some ligands and your metal are going to have some changes in the oxidation state from higher state to lower state. That's the basic definition of reduction and also oxidation. So look at these. We have eta 5 of. So we could see some reactions on this tantalum. So eta 5 C5H5. So this is reductive elimination for the forward reaction and oxidative addition for the reverse reaction. Okay. So this tantalum will be having some reduction in the oxidation state from 5 to 3. And then for the reverse reaction, it will be 3 to 5. The forward one is reductive elimination, and the reverse one is called reductive, oxidative addition. So that's all for today. We have learned 4 types of chemical reactions involving organometallic compounds. We have learned substitution reaction. It can be associative or dissociative. We have learned about insertion reaction. It can take place when you add newly substitute the ligand with the newly added one. It can be carbonate, it can be sulfur dioxide. And the third one, we learned about oxidative addition. And the last but not least, we learned about reductive elimination. I have asked a few questions just now, and those questions can be answered in our Padlet. Thank you very much for your kind attention. See you.